Okay, welcome to another podcast of Math 330. We're going to talk about ideas we're going to have to use in Chapter 1, Section 6. In this chapter, we're going to learn about 5 different methods for solving first order and second order differential equations. We're going to learn about 3 distinct substitution methods, a method called the exact method for solutions, and a reducible method to turn a second order differential equation into a first order so that we can actually solve it. So let's get started. Oh, I just want to give everybody a warning. There's going to be a lot of calculus that we're going to have to do with this. So you might want to pause it, rewind it, go back until you understand how to do the calculus. All right. Started. The first substitution method. Okay, it really doesn't have a name. I just call it method number 1. And basically, why are we doing these substitution methods? We basically, you'll run into some equations, first order equations, and where they are not separable and they are not linear, and the methods that we have learned so far fail at solving these differential equations. But we don't want to create any new ones. We want to find a substitution that turns them into a separable or linear differential equation. Alright, so these types of differential equations are usually considered to be nonlinear types of differential equations. Alright, so here is an example of a first order differential equation. And if you can see, the derivative is equal to some function that has this characteristics where you have an ax plus by plus c function that's easily discernible inside the derivative. So let me show you an example. So here is a first order differential equation. This is not separable. This is not linear. It's got this function, and it's got the pattern we're looking for. A is 1, B is 1, C is 1. It matches this up here. So if you can find a differential equation like this, there is a substitution we can use. We want to make V equal to this. Okay. So to do that, we need to also figure out what the derivative of V is. And so if we do that with respect to x, we get 1 here, we get the derivative with respect to y with respect to x, and then that's a constant, so that goes to 0. We can solve this last expression here for the derivative of y with respect to x in terms of v. And then what we're going to do is plug it right back into that, and then we're also going to take this information and replace that with v. If we do this and do some algebra, well, actually not that much algebra, we get this differential equation. So let's write this out a little cleaner here. So we do some algebra, we have this. Now this is a separable differential equation, and we know how to solve that. So we'll separate it, and there's the integrals we have to do, and we're going to integrate both sides, but we can't really integrate this. This isn't easy to integrate, so we're going to do this substitution. So this is where the calculus is going to get kind of hairy. So in order to do that substitution, I have to figure out how dv is related to du, and if you do that, do some algebra, you get this expression. So I'm going to plug that back in, and so now I can integrate this quite easily, and I can integrate this quite easily, and if you do that, you get this expression. You might have to do some algebra here, some algebraic manipulation to make it easier to do also. But this is that integral. Well, again, I can plug what u is back in here. U is this. I plug it back in, I get this. Alright, so, but v has been substituted, so if I plug in my v, this turns out to be the solution for this differential equation. And yes, it does take a lot of calculus to get this done, but we can solve it without having any other methods to use. So let's go on to our next substitution method. Now this one has a name. It's called heterogeneous equations. Okay, the big question I get, you notice how I don't have the ax plus b plus c, or ax plus by plus c format here. So that's a big indicator that that first method won't work. So this method, we need to use this substitution. So you want to try to arrange the equation to see if this will work. So we're going to have to do some algebra. So this, but by definition of our substitution, y is equal to this. So what we have to do is plug it back in and then do all the calculus. You're going to have to take the derivative here and do some algebra to rearrange it. And if you do that, you can rearrange it into this expression. Okay? Now, technically, this is a separable differential equation. You see, you have all the v's over here, and you only have one x by itself. But you're going to have a hard time doing the integral unless you find a common denominator here, add them together, and if you do that, you get this expression. And then we can separate it. So if we separate it, we'll get this integral for the v's, we get this integral for the x, and we can do this integral quite easily. This integral requires a substitution. So I'm going to use u to be this, and then when I find, and then you do the normal techniques. You find your du, you determine what your dv is, you plug in dv, you do all the manipulation, and it turns out to just turn into this integral. And we can do that integral quite easy. You should be quite familiar with that now. So if we do it and then plug in what u is, we get this expression. So I've got to find out what v of x is. So I have to apply properties of logarithms to get this into the power, and then I take the exponential of both sides, and I get this expression. So my constant c now is a different constant called c1 because of taking the exponential of both sides. And now we can do some algebra and some more algebra. I have to get rid of the square root, so I need to square both sides. And if we do even more algebra, I get this expression. Well, let's plug back in what v of x is. That is y of x over x. I'm moving the constants around right here, and this is a constant. I have no idea what it is, so I'm just going to call it a different constant. And so now I got this expression. Let's substitute in for v. We get this expression. Let's multiply through by this x squared. If we do that, this ends up being our final solution. I cannot remove the x of the y's from the x's here. It's just not possible. So this is your solution. And you would find the constant by plugging in an initial condition, but this differential equation doesn't have an initial condition. So that was substitution method number 2. And we're we're on to substitution method number 3. And now these equations have a name. They're called Bernoulli's equations. And they almost look like a linear differential equation except for this extra y of n term here. And that's how you detect it. Is the y of n there. So if you detect these type of differential equations, so here's an example. So Rn here is just 3. So the substitution you have to use is this. So v has to equal y of x to the 1 minus n power. And since Rn is 3, we get this substitution for this problem. So what do we need to do? Well, we need to plug it back into this and see what happens. So I have to take the derivative of my substitution, solve for what my derivative is. If we do that, we get this. Now I take this, plug it back into here. I solve this for y of x. So there it is. I'm going to plug that back in for all my y of x's, and if you do that, you get this expression. Now, just looking at that, you would say this is much worse than this expression. Well, not really. We want to make this look like a differential equation we have experience with, so we have to get rid of all these coefficients and terms that are multiplied times the derivative. If we do that, it turns into this. Now, this is a differential equation we can solve. It is a linear differential equation. Our p of x is this. Our q of x is this. And we can find the integration factor. If we find the integration factor, which is we integrate this with respect to x and take it to the exponential power, we get this as our integration factor. So we take that, we multiply it by that, and we get this expression. This is a total derivative. Here's the derivative of v, and here's the derivative of 1 over x to the 4th power. So I can rewrite it as this derivative times that, and this is a separable differential equation. So, we did a substitution, we produced a linear differential equation, we found the integrating factor, and now we've reduced it down to this separable differential equation. So if I separate it and integrate both sides, we can do these integrals quite easy. We get this for the left-hand side, we get this for the right-hand side. I want to find v, so we're going to have to solve for that v, and that we get this expression. Well, what is v? This is v. Now we can solve for y. So, if you do all the algebra, we have a solution right here by just doing a substitution method. This is the end of the substitution methods for doing first-order differential equations, and they tend to show up, I don't know, 15 to 20% of the time. It's kind of nice to know about them, but in order to do them, you have to know how to solve a separable differential equation and a linear differential equation using the integrating factor. And so we're going to go on to a completely new differential equation method called an exact differential equation. And an exact differential equation shows up in this form. You got some function we're going to call m of both x and y, and it's multiplied times the dx component, and you add that to some function called n that it could be a function of x and y multiplied times dy, and that equals 0. This is actually the total derivative of a function that is equal to a constant. That's why this side is 0. So you can rearrange this to look like this, so you have to be familiar with both terms in order to get this done. So now, to guarantee an exact differential equation, this condition must be true. So you have to know how to take a partial derivative of the function m and a partial derivative with respect to x of the function m. If this condition is true, then we can apply the exact solution method. So let's do an example. So here is an exact differential equation. Here is m, right? This is m because it's by the dx, and here is n because it's by the dy. So we have now we have to take the partial derivative of y with respect to take the partial derivative of m with respect to y. So we have to take the derivative of cosine x, but it is just a function of x, and you treat all functions of x as constant, so that's 0, and the only thing that appears is the derivative of log of y, and that is 1 over y. So now we have to take the partial derivative with respect to x of n, which is here. So we look at this, and when you do partial derivatives, anything that's a function of y is considered a constant. So here, we only have 1 over y, which is constant. I can factor it out front. And then I have the derivative, partial derivative of x with respect to x, which is just 1. Again, here, there's no x, so that's going to be 0. So this is equal to 1 over y also. So now this condition is true, and so this differential equation is an exact differential equation. And I can apply the exact solution method. But what is the exact solution method? It is this. I'm going to claim this function f that I took the derivative of is the integral of m with respect to x times dy. Now, since m is a function of both x and y, when we integrate it, we're going to treat the y's as constants. And since we're treating the y's as constants, I have to add an integration constant that is a function of y. So let's do this. Here's my m. I'm going to do this integral. Well, I have to integrate cosine x dx. Well, that's equal to minus sine of x. And then I have to integrate this function that just has y in it. Well, that's a constant. So that will factor out front, and I will just be integrating dx, which gives me an x. And so this would be my answer. I have the integral of sine, integral of cosine of x here, and this is the integral of log of y dx, because this is a constant, and I'm going to get an x out. And then I have this integration constant that I want it to be a function of y to handle any changes in y that could occur in this function m. Now, the other condition that has to be applied is that the partial derivative of f with respect to y has to be equal to n. So, well, what is f? I've got it right here. So, I'm going to take its partial derivative with respect to y. Well, there's no y here, so that's 0. That's why it's not down here. I have a y right here, and I have an x, but x's are treated as constants when you're taking the partial derivative with respect to y. So that factors out front, and I take the derivative of log of y, which is 1 over y. That's that term. And then I got to take the derivative of g, which would just be g prime of y. Right here. There we go. And that has to be equal to n. And here's n. There's n up here. Here's n down here. And you find out that you have this x over x divided by y term here, this x divided by y term here, and they're going to cancel. And you have this. Well, this is a separable differential equation. I have a function g and dy. I can separate it and integrate both sides. If I do that, I get this expression. So now I know what g is up here. And so my solution to this is I'm going to take my g, I'm going to just plug it right back up into here, and this is my solution to the differential equation right here. Alright, one last solution method we'll talk about so far. This is the reducible second order differential equation. So far we've only been able to solve first order differential equations. This is the second order. And we only have solution methods that deal with first order differential equations. So I'm going to make a substitution that turns it into a first order differential equation. So I'm going to make this, call this new function called g of x. It has no relation to the other g we were doing earlier. Sorry, bad choice of variables. And I'm going to claim that g is equal to the derivative of y with respect to x. If I do that and I plug it back into here, I get this expression. Well, I still have some y's here, but I don't have any derivatives to y's here. So what I'm going to do is apply a trick. I'm going to do some algebra. I'm going to move the y over to here. And then I'm going to separate my derivative of g with respect to x and multiply by a factor of 1. And this factor of 1 is going to be dy over dy, and put them over different spots here. So I got this derivative of g with respect to dy, and now I got a derivative of y with respect to dx. Wait a minute. That's this right up here. I know what this is. This is g. So I've substituted into this form, and now this is separable. I've got a y dy here and a dg here. If I separate it, I can separate it into this expression. Now I need to integrate both sides. And if I integrate both sides, I get this expression. This is going to give me g squared, 1/2 g squared. Here I integrate 1 over y cubed. So I get this expression plus c. Okay, so thing is, I have to figure out what g is because I know what g is up here. So let's do some algebra. And you do some algebra here, and we find that g is this. So I'm going to put that, I'm going to put back what g is. And so now I have another separable differential equation. But before I separate it, I want to do a little bit of algebra to do that allows me to do the integral a bit quicker, let's say. Well, easier to recognize, I should say. So I'm going to multiply by this factor of 1, and then I'm going to move this top factor inside the square root. And so it becomes here, and then I'm going to multiply it through this expression. So I get this expression here. I'm going to bring this one over to this side. And so now this is a total separable differential equation. I bring all my y's over to this side. I bring all my x's over to the right-hand side. I integrate both sides. Well, this integral is going to take some more calculus work. I need to make a substitution. If I make this substitution, then I can reduce the integral to look like this. Okay, and now I can integrate that, at least the left-hand side, quite easily. Now, and if I do that, I get an expression that looks like this. Now you see I have these two constants of integration, C1 and C2. That's because I started with a second order differential equation. And so I have to have two initial conditions to allow me to solve this. So let's put u back in. So that's what I used for u. And now the idea is to find y. So let's do some algebra to find y. So multiplied by C1 on both sides, squared both expressions, added 1 to both sides, divided by C1 on both sides, and I get that y is equal to this expression. And you're like, wow, that was a lot of work to get this answer. And I would agree, we've done a lot of calculus in this podcast. But technically, you might not be used to doing all this calculus, but you've all done it before. You just need to practice it a little bit more. Sorry for being so late again, just didn't have the time to get it done. So, I'll see you in class tomorrow. Bye.